In this video, we're going to take a look at phase lines and bifurcations for differential equations. So this method, or this approach, concept, whatever you want to call it, applies to autonomous differential equations only. And so what that means is these are differential equations of the form DYDT equals f of y. And so that basically tells us that we are only going to consider differential equations that are strictly functions of y. If a differential equation is a function of t, then this method is not very valuable and can certainly lead to misleading results. So here are a few autonomous differential equations: 0.2y, 0.03y times 1 minus 10 over y, 1 over y, and sine over y. So all of these are considered autonomous because they are self-dependent, or the rate of change in the dependent variable only depends on the dependent variable. Now keep in mind that a differential equation is a change in the dependent with respect to a change in time, so this still does dictate what happens over time. It's just the value or the size of that rate of change does not depend on the current value of t. So when we move on to look at a possible case of this, the first thing we want to do is to take a look at equilibrium values. So this one in particular will equal 0 when either this term is 0 or this term is 0. So when y is 0 or when 1 minus y over 4 is 0. And this is considered a logistic differential equation, used often to model populations so that we have what are called carrying capacities. And so in this case, we have 1 equals y over 4, or y equals 4. Okay, so we have two equilibrium points, one at y equals 0, one at y equals 4. Now, from the existence and uniqueness theorem, this function is continuous everywhere, and so is its partial derivative with respect to y. In other words, any initial condition that I pick, y of 0 equals y0, or we can alternatively write this as t naught comma y naught, every single initial condition is going to have a unique solution because, again, we need to check for continuity. So a solution exists and it's unique for a differential equation at a given initial condition if DYDT is continuous at that initial condition, which it is, but it's also continuous everywhere. Moreover, you could actually write this differential equation as y times, or y minus 1/4 y squared by distributing in y into both of the terms in the parentheses. And so this is actually a quadratic function, and what we know about quadratics is that quadratics are continuous everywhere. And the partial of DYDT, which I will just call the partial of f of y with respect to y, is equal to 1 minus 2 times 1/4, which is 2/4 or 1/2, times y, and that is also continuous everywhere, because if you think about this function, this is a linear function, or the differential equation is linear, which means it's continuous everywhere. This then implies that no two solution curves can intersect for different initial conditions. This is important because if I do have equilibrium points, then that means I have equilibrium solutions. For example, y of t equals 0 is a solution, and so is y of t equals 4. And what that means is that no solutions can cut through these, and I'm going to claim that solution curves are actually asymptotic to the equilibrium solutions. So they can't intersect, which means they're bound, and any solution with an initial condition between y equals 0 and y equals 4 is bound between y equals 0 and y equals 4. So let's sketch let's do a sketch of y versus t. So y versus t, all we know so far is that the equilibrium values are going to be, let me change my color here, whoops, back up. Having a little bit of trouble here. Okay, whoops, one more time. And we know that y of t equals 4 and y of t equals 0 are equilibrium solutions, which means in the y versus t sketch, if y is ever 4, then y will be stuck at 4 because dy dt is going to be 0. So that means we have an equilibrium solution, a horizontal line. So any initial condition that involves y equals 4 will result in y being 4 for all time. And similarly, if y equals 0 ever, then the value of y will be stuck at y equals 0 for all time. These are actually solutions. If you pick an initial condition on either of these two straight line solutions, then you will ultimately result in staying on that straight line solution. So what we're also arguing here is that now our differential equation is going to be positive or negative within these intervals, and we can do a quick check by looking at the intervals that we have. Well, we have 3 equilibrium solutions, so if y is less than 0, dy dt will have either a positive or negative sign. If y is between 0 and 4, y will have a different sign, potentially, and if y is greater than 4, then there will be another fixed sign in that interval. So let's say y is negative. Well, if y is negative, that means this term will be negative, and if y is negative, that means this term will be 1 minus a negative, which is positive. And so the result of a negative times a positive will be that dy dt is going to be negative for y less than 0. So we're arguing, or my claim was, that we're asymptotic to y equals 0 as t changes. Well, if y is going to be decreasing because dy dt is negative, that means y is going to be going down, and so that means it must be asymptotic up here, and it must decrease something like this. And so we can sketch a bunch of solution curves in this interval because we know that they're all going to behave very similarly. And now if y is between 0 and 4, we'll find that the sign is positive, and if y is greater than 4, we'll find that the sign of dy dt is negative. And we'll do a very similar analysis here. If y is positive, then the first factor is positive. If y is positive here, well, if it's between 0 and 4, then this will be a fraction that's less than 1, and 1 minus a fraction that's less than 1 will be positive, and positive times a positive is a positive. Similar kind of idea holds here. So if between 0 and 4, dy dt is positive, that means it's going to be asymptotic to the equilibrium solution. So if I pick an initial condition there, then from the bottom it'll be asymptotic to the bottommost equilibrium point, and at the top y will be asymptotic there. Now if I pick another initial condition, again I'll get a very similar behavior, something more like that. Or if I pick something way down here, I'll get something more like that. And so they'll all behave very similarly. It just depends on what initial condition we pick. Same kind of concept here. And now if I pick a value of y greater than 4 as my initial condition at time 0, then I'm going to have a decay. And that means that if I'm going to have a decay, if I start up here, then we're going to have an asymptotic behavior relative to y equals 4. Same thing way up here, except similar behavior. It'll just take a little bit longer to really converge. So that's how we would kind of sketch the solutions just based off of that. Now, this is kind of a general rule that we're going to kind of accept at this point, that we do have this logistic behavior, this elongated S shape of solutions if a solution curve falls between 2 equilibrium points. It's got to be asymptotic to both values. So what we can actually do here is, since these solution curves are essentially horizontal shifts, what we know, if the differential equation only depends on y, then for any given value of y, the slope lines are fixed. So in other words, if let's say I sketch t versus y, and I know that for this value of y right here, I get a slope vector that looks like that, then that means that slope vector will be all the way across. Trying to draw this exactly the same, that slope vector will have identical incline or identical slope all the way across for all t at that particular value of y. Similarly, if here I have a horizontal slope, then here, I'll also have that. So these are all going to be horizontal shifts, because if this guy looks like this, then this guy's going to look like that, and this guy's going to look like that, and they're all going to be very similar at that same value of y. They're going to have the same slope right there, and right there. So at this point, having a t-axis is unnecessary to understand the long-run behavior of y over time. In other words, if we know that the slope is positive within an interval, then all we really need to do is indicate that the slope is positive within that interval. So in other words, we're going to describe the phase of y as increasing or decreasing. And the way we'll do this is we will actually go ahead and just draw the y-axis, because again, the t-axis just kind of shows us more of the qualitative behavior over time. But the phase line, which will just be like a y-axis without the t-axis. So I'm not going to draw a t-axis here. This is just a y-axis. And all I'm going to label on here is the equilibrium point. So I know I have one here at 0, and I know I'm in equilibrium when y is 4. And what I also know is that when y starts between 0 and 4, then y will increase towards the equilibrium value of 4. If y is above 4, dy dt is negative, which will draw the value of y back to 4 asymptotically. And if y is less than 0, then I will have dk a negative slope, so y will become increasingly more negative. Now each of these equilibrium points has and this is it, this is a phase line. It just shows what phase y is in depending on what value y takes on initially. Now if an equilibrium point, now notice that in this case it's an attractor. This equilibrium point is considered an attractor because the solutions that start slightly below it or above it get attracted to that equilibrium point. They're asymptotic to that point right there. So we give this guy a name, we call it a sink. If you think about it kind of conceptually, the solutions sink into that equilibrium point, and that's only if the arrows, if you think about it that way, point in the same direction. And this guy is a repeller. It repels solutions away from it. It's asymptotic, and then over time we notice that the solution kind of does that within that interval. And so this guy has a name too that is called a source. The other option, which I'll just kind of draw over to the side here, is if you have an equilibrium point where either you have above the equilibrium point solutions flowing away, and down at the bottom, below the equilibrium point solutions are flowing into it. This is called a node. And similarly, you could also have a fourth case where you have an equilibrium point and you have an attractor from one side, but the equilibrium point is a repeller on the other side. And these are called monostable. If you think about it, from a population standpoint, then they're considered monostable. They're unstable here. They're stable here, and they're unstable up here because they fire away into infinity. And similarly here, this is a stable zone, and this is an unstable zone because if you fall below the equilibrium point, then essentially if this is a population, the population falls into rapid decline. Let's consider another case, dy dt equals cosine of y. Now, one thing that we should be doing when we're looking at these autonomous differential equations is looking at the sketch of dy dt versus y. So in this case, dy dt versus y will give us an idea of the value of, whoops, it's supposed to be y, the value of the slope, whether it's positive or negative over certain intervals. Now we know cosine starts up here at 1, and you can think about this as an algebraic function, y equals cosine of x. And cosine kind of does one of these things. And then it continues on and repeats for all eternity. And we know that the equilibrium points are where dy dt equals 0, and for cosine, these happen at pi fourths, and then again at 3 pi fourths, and this right here is pi halves, and this right here is pi. We've completed one full cycle of the cosine curve. Now, because these repeat, let's see, when do they repeat? Well, they go at pi over 4, and then 3 pi over 4. This is 1 pi over 4, 3 pi over 4, and then right over here, this has got to be a multiple of that because the oscillations occur equally as frequently from bottom to, from concave up to concave down. So this must be then, well, 1 pi over 4, 3 pi over 4, 5 pi over 4. And similar concept goes over here. It's actually symmetric with respect to the vertical axis. And so we would have another equilibrium point at negative pi fourths, negative 3 pi fourths, and so on. So our phase line in this case, now notice that the slope is positive in this interval, slope is negative in this interval between here and here, and then again positive between 3 pi fourths and 5 pi fourths, and so on and so forth. So what I can do is I can sketch this and begin plotting at least a couple of them. So I have an equilibrium point at pi fourths, and then the next one in the negative zone is negative pi fourths, and then negative 3 pi fourths. And I'm not going to draw these forever, obviously, so I'm just going to do a dot, dot, dot to kind of give the idea of the pattern that's taking place here. And then I have one up here just for completion at 3 pi fourths. And I can now go ahead and sketch my directional arrows showing the phase. Now I want to go ahead and label the regions, and I'm going to just change in color here for a second. So by drawing the DYDT versus Y curve, we have a very easy ability to look at it and see what the sign of DYDT is between intervals. Now keep in mind that we're plotting the slope. So the sign of the slope, for example, is negative if y is between -3 pi-4ths and -pi-4ths. So if it's in here, then the slope is negative, which means that the solution function, y of t, will tend downwards. And if y is between -pi-4ths and +pi-4ths, then the slope is positive, and therefore y, any initial condition falling between those two values, will result in an increasing function of y versus time. And similarly, negative here and positive slope here, and this will again continue on. And so I have a source and a sink and a source and a sink, and we will actually have alternating sources and sinks because of the fact that over one interval between equilibrium points, DYDT is positive and then negative and then positive and then negative, and this will repeat indefinitely. So we can say that we have equilibrium points at y equals, let's see here, so we could probably say plus or minus, we can say k pi-4ths, where k is any odd number. So pi-4ths, 3 pi-4ths, 5 pi-4ths, 7 pi-4ths, 9 pi-4ths, and same thing in the negative region. And we have positive and negative ones. So this is a case where we can have potentially infinitely many of them. Okay, well, let's consider why this might be useful. So suppose that in our original model, which is the logistic differential equation, we begin hunting elk at a rate of 0.5 elk per year. So this means that we now have a harvesting parameter, which we'll call a harvesting parameter. Now, since this is right here in elk per year, that means that this term here must be an elk per year. Now, I don't care about the individual factors of that term. One term is anything separated by a plus or minus sign, and then I'm going to subtract off elk per year, and I know I'm going to subtract them off at a constant rate of 0.5 elk per year. Are there any equilibrium points? Well, now the situation becomes a little bit more complex, because when I distribute this out, I'm going to see, like, I can't just set this equal to 0 and factor out a y, because I don't have a y in the constant term. This constant term is throwing things off. So if I distribute things out, I'll actually have negative, oops, this should actually be y over 5. So I have negative 1/5 y squared plus y minus 0.5. And I want to set that equal to 0, and I want to figure out what values of y make the rate of change 0. So the easiest way to do this is going to be to either solve this using quadratic formula, or I'm going to actually go over to a solver, and I'm going to type in that equation, negative 1/5 y squared plus y minus 0.5 equals 0. I'm going to use x just because I think Wolfram might like that a little bit better. And this will actually then solve those equilibrium points for me. And I find out that I have one at approximately 0.56. I'm just going to round it to 0.6 and 4.4. So equilibrium points are at y equals 0.6 and y equals, we said, 4.4. Okay, so that means the associated equilibrium or phase line will be very similar, except now, whereas on that phase line we had equilibrium points of 0 and 5, now we have one at 0.6 and 4.4. So what we actually noticed from our previous example is that the and we can verify this, that the behavior between equilibrium points and outside of these equilibrium points is very much the same, except we notice that the equilibrium points came together a little bit. So those equilibrium points actually squeeze together a little bit more. And so if we wanted to sketch this over time, we could do a very similar thing. We know these are equilibrium solutions, and they would look like this. Oops, more like that, and like that. And so now let's look at a case where we harvest some more elk and see what happens. So we might already have a speculation that as we harvest more, maybe those equilibrium points come together even more. And let me set this to be 1 now, because now we're going to assume we're harvesting 1 elk per year. So I'll come over here, and I'll set this to 1. I have -0.1, but that's fine. And now I get 2 solutions, and I'll click approximate form here, and I get 1.3, 1.4, and 3.6. So y equals 1.4 and y equals 3.6. And I'll draw my phase line, and again I notice that they've squeezed together even more, 1.4 and y equals 3.6. And again, I know that the slope behavior shouldn't change, and I can just verify that. What I can actually do is I can graph DYDT and see that it's positive between those equilibrium points. In other words, DYDT is above the horizontal axis, and if y is less than 1.4 or greater than 3.6, the sign of DYDT is negative. And so that helps me justify doing what I'm doing now. So the behavior should still be the same, because we argue asymptotics, and asymptotic to 3.6 initial conditions above, and asymptotic to 1.4 for initial conditions below. So see, the behavior is going to be very much the same, and if we did a slope field, we notice that all these solutions are very much similar behaving because of the fact they're autonomous. The value of the slope does not depend on time, but instead on the value of y. Okay, well, let's consider one more case, and suppose we're harvesting at 1.5 elk per year. Okay, so that just changes our model. Our value here becomes 1.5, and now I need to find equilibrium points, so I'll change this to 1.5. And if you're familiar, which hopefully we are all familiar somewhat with quadratic functions, if I change the value of c, I'm changing the value of the vertical intercept. So we can see negative 1.5 is right there, but now the entire DYDT curve is below the horizontal axis, which means I have no equilibrium points. And as a result, that means what I'm going to draw is a line. So I'll say y equals, I don't know, does not exist, or they're non-real. And now my phase line doesn't have any equilibrium points on it, and it doesn't matter what the value of y is along this axis. So here's the y-axis, here's DYDT, and my entire DYDT curve is below that. So for any value of y, DYDT is negative, which means that that is causing y to decrease indefinitely. Well, what does that mean in terms of our scenario? Well, that means that regardless of what population size you start with, if you're killing 1.5 elk per year, appropriately scaled, then your population is headed into collapse. Simple as that. Now, we might begin to think about, well, let's summarize these phase lines. In other words, what did we observe? Well, if we look back at our original scenario, we noticed that we had 2 equilibrium points, and those were 0 and 5. So what I'm going to do here is I'm just going to I'm going to sketch this for, and what I'll do is, just to make this more concise, I will write out the differential equation, and then I'm going to add this, what I'll call this harvesting parameter. I'm going to call that alpha. I'm going to say that this is the elk hunted per year. And we're subtracting that off because, of course, that's going to contribute negatively to the population rate of change. And I know that if alpha is equal to 0, then I'll have equilibrium points at y equals 0 and y equals 5. And now I can also sketch one for y equals 0.5. Or sorry, alpha equals 0.5, so hunting 0.5 elk. And I noticed that those came together a little bit more. And those equilibrium points, if I back up a little bit, were 0.6 and 4.4. So I will go ahead and label those. Y equals 0.6 and y equals 4.4. And then I know that if alpha was equal to 1, I'm going to try to keep the spacing between these equal so that I can see that there's a consistent change in alpha. There were none. And between here, there were positive rates of change and negative rates of change and negative rates of change down here, and then solely negative rates of change. Well, if I looked at different values of alpha between 0 and 0.5 and 0.5 and 1, because there are infinitely many of them, what I would actually observe is that if I connected all those dots, I'd actually see something like this. And somewhere over here, we lose an equilibrium value. So at this point, whatever this value of alpha is, and I don't know what it is because we'd have to actually search for it, but this value of alpha results in having exactly one equilibrium point. And that means that from above, the rate of change is negative, and from below, the rate of change is negative. So suddenly we go from having this being a source and a sink and a source and a sink to this single equilibrium point being a node. And then suddenly we don't have any equilibrium points, so we've lost classification of any equilibrium points altogether. And this poses an interesting problem, because if you start to hunt alpha equals question mark number of elk, then if you don't start off with more than 4.4 elk, your elk are going into extinction, or whatever this equilibrium point is, excuse me. So that means that if I increase the hunting beyond alpha equals whatever this amount is, somewhere between alpha equals 0.5 and 1 elk per year, then I am going to have complete chaos in terms of my population. The rate of change of the population will always be negative if you're hunting more than alpha equals whatever this number is, number of elk. So let's take a look at this. What is that number? Well, we notice that the graph of this guy, and what I'm going to type in here is x. I'm using software called Desmos, as you can see in my address bar, and I'm just going to type in x times 1 minus x over 5, and then I'm going to type in minus a. And immediately I'll get asked if I want to insert a slider, and I'm going to insert a slider. And I can see that as I begin to vary that value of a, that is shifting the parabola down in the DYDT y plane. So eventually somewhere over here, between, that was between 1 and 1.5, somewhere in between there, I am getting a single equilibrium value. And what I can do here is I can actually snap that into place and see what happens to those 2 points as they come together. And it seems to be the case that right at about, I don't know, between alpha equals 1.2 and 1.3, I suddenly lose an equilibrium point. So this guy right here has a special name, and this is called a bifurcation. A bifurcation is can be called a bifurcation point or bifurcation value, and it's said to occur when there's a significant change in long-run behavior, which is a change in quantity or quality of equilibrium points. For the most part, both things happen. We lose a quantity, we go from having 2 to only having 1 equilibrium point, and the quality of that equilibrium point changes as well. Its classification goes from sink, source, to node. So that behavior has changed entirely. So let's look at a general function. Let's look at a function that I'm going to go ahead and sketch here. So we have some differential equation that is potentially, I should say, not a function of t, but is a function of y and some parameter alpha. The way we can think about this is this could be a hunting parameter. In other words, we are trying to decide how many elk we're going to allow to be hunted. And so we can allow alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, or alpha 6, or anything in between. And we want to look at equilibrium points. So at any given point, if this is a phase line for y, then in this case there are 4 equilibrium values. We don't really know what happens in between them. And then over here there are still 4. And at any given point between alpha equals 1 and alpha equals 2, there are still 4. And then suddenly at alpha equals 3, we drop from having 4 to having 2. So that means this is a bifurcation value right here. we lose the quantity of equilibrium points. Similarly, at alpha equals 4, we lose an equilibrium point. So again, we have a bifurcation. And then at alpha equals 5, we gain one. So that's a bifurcation. And then we lose one at alpha equals 6. So that's also a bifurcation.